Hello, I'm Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video is going to take a look at the C++ Standard Template Library Linked List Class, otherwise known as STL::list of type T. So I already have a lot set up here under the hood. I've got my Visual Studio environment. I've included IOStream and list. I have my cppreference.com website open, and you can see the same information in my favorite book when it comes to this kind of stuff, the Jasudis, Nikolai Jasudis book, C++ Standard Template Library, 2nd edition. Maybe there's a 3rd. I haven't checked into it, but this works just fine for what we're going to be doing today. So what is a list class? I've already covered the high-level understanding of what a list is. This is that medium-level understanding of just getting the standard template library to work, and then my next video will be getting this thing working in a more in-depth manner, creating our own custom list class. So as we've discussed previous, a list is a container that supports constant time insertion, meaning as long as you know exactly where you're going to insert something, it takes always the same amount of time to insert that new value into your linked list, as opposed to something like a double-ended queue or a vector, where it all depends on where in the vector or the double-ended queue you add your information. So let's see, adding, removing, or moving the elements within the list does not invalidate iterators or pointers or references or anything like that. And that's again because when I'm dealing with a vector, I have a contiguous block of memory. And if I add something to it, and I'm like, now I'm overstretching my bounds, I have to create a whole new memory structure, copy everything over, and add the new guy in. So anything that's pointing to all of that stuff in the old array, that could be kicked out and that could be invalidated. But in a list, basically every time I new up something or I'm adding a new element, I'm newing up some place in memory, which is completely different from every other memory, and it's not contiguous in any shape or form. I like to use, growing up in the era I did, Duck Dodgers in the 24th and a half century, where there's a map where just data's going all over the place trying to figure out where to solve the problem of trying to find planet X. It's the same kind of thing. Like, you have no idea where the next item in memory is, and it's just thankful that you have a pointer to that stuck inside of the current piece of information that you're trying to find. So that's where we're coming from here. And just say, like all the other templated types, T is the data type that we care about. And if I just create a brand new empty list of type T, which is int in this case, here is my empty case. A is an empty list, and of type T, which is type int. So they say, if you've been through a lot of these other videos that I've made when it comes to vectors and double-ended queues and whatnots, then you're pretty familiar, because again, the standard part of this is a lot of the functions, a lot of the functionality here is very common and is very similar, if not identical, to things you've already seen. It's just the data structure under the hood is different than the ones that you've already learned about. So when it comes down to constructors, it's the same idea. There's a ton of them. Here's an empty list. Here is a new one that can initialize values, just like we're expecting. That's my initializer list version of that. I can use a copy constructor. And remember again, as I say every single time, there's a huge difference between these two lines of code, lines 8 and lines 9. Line 8 uses the copy constructor because C does not exist in that current moment of time. It's being constructed. It is that line of code is constructing item object C, but line 9 is not. So 8 is a copy constructor, 9 is the copy assignment operator. So when it comes to this, maybe there's a few other using iterators. I could go ahead and say, if I wanted to set up another linked list of D and just say, okay, I want to use a.begin and a.end. Maybe that's not the best case. Maybe I can use the B instead, since that has some actual elements in it. And so you can use things like that. And so if I run my program, it doesn't matter what it looks like, but D holds size of 5 with values 1, 2, 3, 4, 5, because it went over to B, which has 5 elements, and basically copied everything over element for element into D. So everything has its own unique version of that list. So when it comes to this, there's a few others, but that's basically it. let's say, can I don't know, it's one of those just try it out. Can I make a list, like a vector, where I say, give me 10 elements? Can I do that? And the answer is, it looks like, yes, I can. And so in this case, it should all init to 0, 10 elements, all initialized to 0. But what if I did it just like I did with vectors, where I set them all to 3? Does that work as well? And the answer looks like to be yes. So that interface is the exact same, and that's right here. Where is that one here? Count, and then allocator and stuff like that. Where is it? Where's the one that has the T type? I'm not finding it. Here, count, and then value equals T. And then this is count value equals value. So these are the explicit constructors here. Copy constructor and whatnot. So yeah, that pretty much covers everything when it comes to just constructing the thing. And again, that was the copy assignment operator. The destructor we never have to worry about because that takes care of everything under the hood. Once these lists go out of scope, all of the memory that has been allocated under the hood is brought back, and the operating system is given that memory back, so we don't have to worry about any of that kind of stuff. But just like before, we have access to the front element and the back element. So like in the case of B, if I just wanted to print out b.front, that should give me the 1. And then the back element should give me the 5, or maybe not. Let's find out. And it does, 1 and 5. And there's a difference between back and end, right? Back is the element, the actual final element where, like in this case, the 5. And end is actually one past that. Which way do I go with my hand? But because 1, 2, 3, 4, 5, end, because we have to process through all of the elements. So 1, 2, 3, 4, 5, we have to keep on going, and then the end iterator is 1 past the end of that list. But back is the actual final element. So end is always 1 element past back. And this this presumes there's elements. So like for A is an empty list. If I run this, there's my crash, there's my, this hits the, is this the assert? Oh, that's an actual, no, what is that? Is an assertion. This isn't an exception, this is an assertion. There's no way around this, there's no way catching this. This is not, since this is an assertion, not an exception. So you gotta watch out for these kind of things, because there's no way out of that. Okay, so I said, yep, oh boy, all that fun code under the hood that PJ Plowder wrote. Is it PJ Plowder? Nope, he won't show us his name here, but I think it's PJ Plowder. All right, so that's the front and the back. And so what else is there? We'll come back to the iterators here in a little bit because we need them for all the modifying functions. But for in this case, empty and size are the big ones, right? Because like empty, if a.empty equals true, stdc out, a is empty, right? And in this case, A is empty, so it will print. Oops, oh no. Just gotta restart my program. What did I do wrong here? What did I do wrong here? Hold on one second. Let's see, rebuild. Let's see what I'm looking at here. Oh, I'm at end line. Oh, yeah. It is, what time is it? 1:22 in the morning. It is a long night of making videos and doing stuff, so sorry about that. So see out end line, and oopsie again, right? So what is this? We have a runtime error because of this front. Let me get rid of that thing. Let me get rid of this stupid thing. Oops, come on. Always fighting the compiler, starting over, run it again. And finally, there we go. There's my A is empty. It prints out because the thing is empty. And if I replace this with a B, and run this again, of course it won't print anything because B is not empty because B has 5 elements. So there's empty. If I want to use size, if B has 5 elements, oops, I should just, I'm just going to leave it. That's hilarious. If B size is 5 and A is not empty, that is as meme-tastic as you can get. But of course, if it's not the case for A, it won't print anything because the size just returns an unsigned int, and there you go. A is 0 size, it's not 5 size, so there you go there. Okay, so then empty in size. So now coming back to the whole idea of iterators, so this is where, like with vectors and all that kind of stuff, you don't necessarily have to use iterators, but the only way to progress through a list is using iterators, because I cannot go ahead and just say print out like I can for vectors or anything like that. I just can't go ahead and say, okay, print out the fourth element or the second element of A. There is no definition of square bracket array access to a list, because a list, it's not contiguous. It's not an easy mathematical operation to figure out where the next element in memory is, because everything is just kind of all over the place. So because it's not trivial for the computer to find, it's not going to allow you access to that. You could write the code to figure out where element 2 is, but that's on you to figure out if you want it to occur that way. So you can't just have random access when it comes to lists. So if I could go ahead and do the range-based for loop like I've done for everything else. So for every int I that's part of B, I can go ahead and I can print out I in a space. And so this will print out 1, 2, 3, 4, 5. There's my 1, 2, 3, 4, 5, as you can see. And so I can use the range-based for loop, but I cannot use that square brackets or anything when it relates to that. So the other way to go about doing this is to set up iterators. So I can say, okay, give me a list int. Oh, come on, list int iterator. Oh boy, iter equals b dot begin. And then I can use a while loop for this. You can use a for loop too, but you can use a while loop just the same. While iter does not equal b.end. Come on, this is not a good night for this. Star iter, just like before, and printed everything out. And this should print out there. Oops, oh boy. Because I used a while, not a for loop. Right now, hilarious. It's just printing out ones forever and ever and ever. And that's because I did not ever touch iterator, and like all the other iterators, I need to do a plus plus. So there's my 1, 2, 3, 4, 5, like I was expecting, instead of printing 1 infinitely. And so again, because I'm not modifying anything, it makes more sense for me to use the const iterator and then use a C begin and then use a C end. And you say you won't notice anything on the printouts, but again, the whole const correctness portion of C++, it makes more sense to use the const iterator in these cases. So I can also have reverse iterators. Oops. And that's why, again, there's 4 different types of iterators. You can have, do I go forward or backwards? That's question 1. And do I do I have constant or not? That's the other one. So 2 different options, and that's 2 to the squared power. That's why there's 4 different types of iterators, 8 different, completely different iterators. So I could say R begin and R end here, and then it's interesting, right? Like every other time where it's plus plus iter, but because I'm starting at the back, forward is actually backwards, so I don't have to do a minus minus iter in this case, because I'm starting from the 5, and to me, forward is the backwards from what I usually normally do. Okay, so that covers iterators, empty size. So now the rest is just filling in the gaps for all the modifiers and all the operations. And these operations here are a little more specific to linked lists than you've seen in anything else. So I can just get rid of this for the time being here. So like a clear, of course, I could just clear out and say b.clear. Or let's see, yeah, I can do that. Yep, b.clear. And so that will eliminate every element. B had 5 elements a second ago. B is 0 when I get to it here, right? So here, maybe this is the point to do the breakpoint and run it again. Run it a second time. And you can see, it doesn't matter what is on the screen here, but I go, okay, B has 5 elements, 1, 2, 3, 4, 5, and B now has 0 elements, which is nothing in it. And again, you got to remember, if you're dealing with pointers and they're newed up, by clearing, you're not erasing or deleting any of that memory, and you're going to introduce a huge memory leak when it comes to the way C++ operates. So you got to watch out for that. Okay, so insert, this is where things get interesting, because like before, you'd be like when I was showing you this in the vector class as well. I can't just go, I can go b.insert, but I can't just do b.begin plus. And for the same reasons, I can't do something like this and just say, okay, b.begin plus 4, and it's the same reasoning, and this is a really, really horrible error that pops up. And this is where templating starts to rear its ugly head here when it comes to reading what's going on and reading the error message. And so because I do not have random access like I do with the vector class, I can't use square brackets, and I also can't use plus 4. I would have to have a legit pointer or iterator to a specific place in the linked list in order to insert something. So begin is perfectly legit by itself, but it's not allowed to add or subtract to itself in the normal manner. And so if I just take this real fast then, and I add an 8 to the begin, you could imagine that when I do for int I is part of b, or I'll make it c since nope, leave it b. And then I can see out the I value in a space. You can imagine the 8 will go up front. And there's my 8, 1, 2, 3, 4, 5. And so like this, if I wanted to put it in before the back iterator, I can do that as well, or maybe I can't. Let's see this. If I can't, what does this say? No instance of overloaded function returns, and that's because back returns an int reference, and a reference is not an iterator. So something like this is not allowed, so I have to have an iterator. And so again, I'd have to have a legit iterator to somewhere else. I'd have to do other code. Oh my goodness, the complicatedness of this. If I wanted to move over for int I equals 0, I is less than 2, plus I, start with an iterator. Oh my goodness, std : list iterator, oops, list int : iterator, iter equals c.begin or b.begin, it doesn't matter, they both share the same stuff here. I can say plus b, and then I can say something like this. I can say, oops, I can't say plus iter, I meant, and then I can say b.insert, and I can use iter, and I can add a 19. So this will go, where does that do now? Look at all that, look at all that fun code. Oh my goodness! But you see what's happening here. It was a roundabout way, but I was able to go and start from element 0 and move over and say, hey, add a 19 before element 2, and that's what this does. Not saying it's easy, and it's like in these kind of cases, you're like, what is the point of all this stuff? Well, the point of a linked list, the point of a vector, is you're supposed to be using algorithms that return iterators. You're like, okay, if I'm like, let's partition this array or partition this list, so all the elements that obey a certain rule go on this side, and all the ones that don't go over here. It's like I can set up iterators, and it will return iterators, and everything will become much more clear if you start using those kind of algorithms that are in a different chapter that we don't. Unfortunately, we don't get to cover in as much depth as we'd like to. That's the reasoning why all of this is occur. Why is this so complicated? Because in general terms, you don't do this kind of work to get to a specific point to insert an element, but just to show you that it's possible. And so the same would go here if I wanted to use the erase. And so if I just print out like this, I can put this in a loop while b.empty is false. Okay, let's do some stuff. So let's print everything out, and let's put an end line in here. But let's see about this. And after I print everything out, how about I go and I said, okay, b.erase, and I say, what do I want to erase? It has to be an iterator, so I can say erase the first element. And so you can see I start out with 1, 2, 3, 4, 5, my full B list, and every single time I go ahead and erase the initial element, and you can see as it works its way down to an empty list, it does exactly that. So erase, as long, that's the great part about linked lists, as long as you have the iterator to the exact location, it's real easy to insert, it's real easy to erase, and it takes almost no time at all compared to vectors and everything else, because the amount of time it takes to add or erase from a vector is completely dependent on where it is in the list, because everything has to be shifted one way or the other to accommodate the insert or the erase. So notice, just like a queue, double-ended queue class, you have pushback and popback, and then if you have push and pop, you also have, for the back, you also have push and pop for the front. And so because it's, when it comes to a list, you getting access to the beginning, the first element is easy. Getting access to the last element is easy. It's just not easy getting to everything else in between. So that makes sense that I have access to those kind of things. So if I go ahead and say b dot pushback 6, and this, again, the push is the only way you can take an existing list or an existing data structure and make it larger than it currently is. Because at this point, because I don't have square bracket access, I can't just go, get me the next element, get me the one past end. It just doesn't work. So I can say push back for a 6, and I can push front for a 0. And you can imagine then I run this one more time and I go up there. The 0 goes out front, the 6 goes to the back, and then just like I did a minute ago, just take off the first element every single time as I go through. Okay, so let's see, I've covered cleared, I've covered insert, we're not going to worry about in place, erase, push, we've pretty much covered all the major modifiers, all the major functions that modify, that mutate the list class, and now the last kind of things here are just these kind of functions that don't exist anywhere else. So let's just say I can sort, I can't sort the same way. Like I said, there's a very specific sort algorithm for list, because sort is not a member function of vector or double-ended queue or anything like that. You can use the algorithm version of that, but this has a very specific version. So I can switch this up just a little bit. A 1, 2, 3, 4, 5, and I can go ahead and put a 0 to the front, or I can even put a 8 in the front. Or I'll just put the 6 in the front and put a 0 in the back, and then I can say b.sort. And I'm right back where I was, but of course it took more effort because the computer has to go ahead and perform some kind of sorting algorithm, some kind of quick sort, or who knows what kind of algorithm behind the hood. But we're right back where we were a second ago. 2, 1, 5, 4, 3 with a 6 and a 0 becomes 0, 1, 2, 3, 4, 5, 6, and just like before, everything kind of kicks its way out. So just when it comes to this, what about uniqueness? So what if I don't sort? Let me change this. Let me add a little bit. Add a 2 and a 1 and a 5 and a 4. And what if I do a b.unique and run this code? And you can see there's my, I pushed a 6 to the front and a 0 to the back. So, so 6, 2, 1, 5, 4. This is everything that prints out the first time. So unique, what does unique do? You're like, what does it do? Removes all consecutive duplicate elements. So we're going to talk about the set data type. We're going to talk about the map data type in future lectures. Those automatically sort the data for us as we're inserting into its data structures. Really kind of cool. But the list doesn't do that inherently. So just because I have duplicate elements of 2s and 1s and 5s and 4s, because they're not right next to each other, they're not consecutive elements, the unique function isn't doing what you might think it would do. So you can see there's my 6, that there's 2 2s, 1 5 4. But what if I throw this sort in front and try it again? And when I do that sort of thing, you see, because it sorted everything out, all the duplicate elements are eliminated that are consecutive. So because there's a 2 next to a 2, that second 2 is eliminated along with the 1 and the 5 and the 4. So we're right back to where we were a couple seconds ago. So let's see, and then so really the last kind of stuff here, you know, say like there's really no reason to worry about merge, because merge, what does merge do? It takes two lists, you put them together, and it eliminates one of them. I don't know, you know, it's one of those things like, for me, like, yeah, it merges two lists together, it takes two separate lists, makes it, especially, you know, because it's supposed to be sorted. So it takes two sorted lists and put them together, and so that the new list is in sorted order. But whatever, you know, one of them is the new one that gets everything kind of jammed in, and then the other one gets erased. So it's you know, it's one of those. Let's see if we can see in this code here. You go, yep, it's not a const reference when you're merging. It's a non-const reference. So left-hand side. There's other videos that talk about what's left-hand side, right-hand side. Left-hand side gets merged into. Right-hand side pretty much gets completely cannibalized and erased out when it comes to that sort of thing. So what do I mean? I guess I can do this real quick here. Let's just set this up and just say, I'll just say std : list int e is 1, 2, 3, 4, 5, and then I can say f is 6, 7, 8, 9, 10. So I can say e.merge f, put a breakpoint in. Oops, I don't know what just happened there. Don't know what that error was. So I can do e.merge f. Oops, where did I define e already? Already, A, B, C, D, E. I'll just call that G just to get it over with. Okay, oops, okay, there we go. So what am I doing here? E, size of 10, F, size of 0, because it took 1, 2, 3, 4, 5, and it merged it in. There's my E. And you're like, okay, that didn't prove anything when it comes to the merging, and it sorts everything together. So when I put a 6, and I put in, and again, these are presumed to be both in sorted order. So let's see, 1, 4, 5, or 1, let's say 1, 2, 4, 5, 9, and 10, and run this a second time. And what do I have? E is size of 11, F is size of 0, and E consists of 1, 1, 1, 2, 3, 4, 4, 5, 5, 9, 10. And if you don't have both lists sorted when you go ahead and do this, you're not going to get results that you're expecting to see. It's presumed that both of these lists are sorted as you merge them in. So this is basically the definition of merge sort. If we'll cover that in the next couple of weeks as well when it comes to recursion and recursive algorithms. And you're presuming the lists are sorted, so when the algorithm can work itself out, so that the resulting list when you merge them together is sorted as well. So let's see. So let's see. Okay, so I can kind of set stuff up here. Let's see what happens. Let's just play around. Last thing here is this remove statement. So let's see. I have E, I have F. I'm going to put that back. E.merge F. Uh-oh. 16877. And I have an assertion. What is this assertion? And I go, oh boy. What does this thing tell me? Thing is telling me cast bool blah 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 blah. Sequence not ordered. So isn't that kind of weird? I mean, I didn't even realize as I was doing it. Like, this thing is smart enough to know that my F is not already in sorted order. So it's going to throw it's not an exception. It threw an assertion, and that is not good because there's no way out of that thing. So, oopsie, I better put this thing back in a different order so that it doesn't yell at me again. So sorted list, merge them together. Try this one more time. And now E has size 11, and there are all 1, 1, 2, 2, 3, 4, 5, 5, whatever. It's all good. So what I'm trying to say here is what happens now if I say E.remove, and I say just a value. So I say remove all the ones. So I can run this again. Oops, I can't. I had a dime for every time I forgot to close down. But I'm going to go, okay, E has size 5. I'm going to merge it in. E becomes size 11. There are 2 1s, and you go remove all the. Well, let's see. What does remove do? Will it remove? What will it do? F10. E size 9. Okay, so it actually removed all of the 1s. I was kind of curious to see if it would only eliminate one of them, but in this case it pretty much goes through the entire list as you see it and goes ahead and says, anytime I see a 1, get rid of it. And in this case, like I said, it removes elements satisfying specific criteria, and it does not mention anything about sorted lists. So it can be, so I could, if I didn't merge it, if I just put a 1 at the end here, and I did not merge, and I try this one more time, will I have a 5 size or 6 size when I'm done with remove? And the answer is 4. It eliminated the 1 that was at the front of my list and the 1 that is at the back. And so coming back, so we can have, so there's a remove if, and that uses all sorts of crazy stuff. You can use lambdas, which we never discussed. You can set up all sorts of stuff to make this thing work. That is not a right now problem. This is just a medium level how you doing when it comes to using the standard template library with this functionality. So that's pretty much all I wanted to cover for this video. Let's see, anything else? Nope, same kind of stuff. There is an erase if, but it's the same deal as remove if. I can erase, instead of, remove, erase, that kind of thing. What is the difference? We'll leave that for another time as well, because there is a difference between erase and remove. And it's hard, it's one of those things without an example, which I'm not going to go into now. It's kind of hard to describe. Alrighty, so as always, thanks for sticking with this. If I missed anything or if I misrepresented everything, please send me a comment or please send me an email to swardb@cod.edu. Nothing is intentional. And always send me any questions. Anything come my way, I'll get back to you as soon as I can. So the next video will cover, since we now know how a high level of what a list does, and now we know at a medium level what the standard template library does, now we need to understand at a low level, behind the scenes, what is the list actually doing for us. So we'll spend a little bit of time, half hour, who knows how long it'll take to do, maybe more, probably an hour or more, to create our own custom linked list class, a doubly linked list, and kind of go through all of the bells and whistles and all of the hoots and hollers of what's going on under the hood every time I use these kind of functions in the list class. So thanks again, and we'll see you next time.